Welcome, ladies and gentlemen, to your section 7.5 notes on properties of logarithms. We have two objectives over here. One, we're going to use logarithms to expand or condense an expression. And then the next thing we're going to do, which is pretty straightforward, but it's really, really powerful, which is using the change of base formula to actually evaluate logarithms. So those are our two objectives, and I'm going to just get right into the logarithm properties. But I think it's really, really important to note that, again, exponents and logarithms are inverses of each other. So if I ever ask you, what is a logarithm? I would hope you would say, it is the inverse of an exponential. Another answer is, what is a logarithm? It's when you evaluate a logarithm, you are finding the power, the exponent. So let me just kind of come over here and remind you about the exponential property right here, where we have a to the m times a to the n. And if I ask you what you do with those exponents, I would hope you would say, hey, you know what, Ms. Bakken? You add those exponents. Well, that is really where the product property of logarithms comes in. So if you notice, log base b, it's m times n, and because of the multiplication, we can separate this into two logarithms where you have log base b m plus log base b n. So there's no magic here. This is completely related to this power property right here because they are inverses of each other. So, and by the way, you can do a reverse as well. You can condense it from this property. So this can go either way. If you have something that looks like this over here on the right, you could switch it over to something that looks like that on the left. And it's all about that a logarithm is an exponent, is an inverse of an exponential, and so they're completely related. Okay, so quotient property, as you probably are going to figure out here, is if I come over here and say, hey, you know what? You have a to the m over a to the n. How can you combine those? Again, I would hope, because you see they're the same bases, you can subtract your exponents. So if you have, again, a division over here with the quotient property, that means then that you can say log base b m minus log base b n. So hugely powerful, these properties, and we're going to be using them a ton. And again, hopefully relating them to the exponentials will make it a little bit easier. The power property is super cool, and it is related to the exponential, but just for time's sake, I'm just going to show you. All you're doing is when you have log base b m raised to the n in general form, you can take and bring that exponent down and put it right in front. So n times log of b to the m. And really remember, a log is an exponent. So log base bm, if you were to evaluate that, that is an exponent. And when you're taking an exponent and raising it to another exponent, you're really just multiplying those together. Okay, so coming down here, let me just say example 1, we're going to expand. And you really want to make sure you read your instructions here. It says use the logarithmic properties to expand the logarithmic expression. So expand means to pull apart, really, right? Or make bigger. So notice that we have multiplication in here between the 7 and the x, and then we also have that square, which is, we're going to use that power property at the very end to use that. So let me just kind of show you how to expand this. So I'm going to go log. I'm going to first use the product property. So log base 3, 7 plus log base 3 of x squared. So all I'm doing is separating that product by using addition. And then the only other thing I have to do over here is that I have this right here, and I know using this last power property that we talked about, we can bring that right up front. So the end result is going to be log base 3, 7 plus 2 log base 3 x. And that is your log or this expression in expanded form. Okay, so let's kind of keep going here. Now notice I'm going to always, and you will hopefully notice this, I'm going to use always the product and the quotient property, the first two logarithm properties before I use the power property. So this one here, it's a natural log, so I'm going to go natural log of x squared, I'm not going to mess with that squared, plus the natural log of y to the fifth. So I'm using that first property that I showed you. Now I'm going to use the last property by bringing those exponents out front. And it's as easy as that. So really, the gist here, folks, is that at the very end, you shouldn't have any multiplication or division in a problem. In the sense of, when I say natural log x, that's not multiplication, that's actually evaluating a natural log x. But so right here, you see how you have multiplication between those two. You don't want any of that, you don't want any division, and you don't want any exponents. Those end up going out front. So it's almost like they're all on the same, like one line, straight across. So this one kind of gets a little bit more complicated, this letter C, because here, if you see, you have multiplication up here, you also have a square root, and then down here you have multiplication and a square, and then you also have division. So usually what students ask is, okay, what do I do first? Well, I will just say this. The first thing you want to do is always the product and the quotient properties. You want to do the power properties last. And the other thing to note, and this is just to keep it very, very straightforward, if it's in the numerator and they're multiplied together, you add them. If they're in the denominator, it doesn't matter if there's a whole bunch of them multiplied together in the denominator. If they're in the denominator, that's technically considered division, and that's when you make sure there is a minus in front of them. So let me show you what I'm talking about. I'm going to go right down the line. Log of y cubed. I have a multiplication between y cubed and square root of z. Now, square root of z, we know, you can't leave it as square root of z. You're going to write it as z to the 1/2 because we want to write it with all exponents. So we have log y cubed plus log, and notice it's all common log, so I don't have to put a base, log z to the 1/2. Now, that's all that's in the numerator. Now I'm going to say minus log 4, because 4 and x squared are multiplied together, so they're kind of by they're each element, that's the wrong factor, is by itself. So log 4. Now this is where you might think, well, plus, because 4x squared is times or multiplication, but that's not the case. What you're looking at is it's minus log to the 4th, because it's the 4 is in the denominator, minus log to the x squared, because again, that's in the denominator. So if you were to condense this or bring this all together, you would know very quickly that what goes in the denominator is the 4 and the x squared. Now, of course, like I said, you want it all on one plane, and you can't have exponents, so let's get those exponents out front. So I'm taking this and pulling it up front, same there, and same there. So we have log, oh, I forgot my 3. 3 log y plus 1/2, my handwriting's getting worse here, log z minus log 4 minus, my handwriting, oh, I'm sorry, you guys, is 2 log x. And that is your final answer. So notice everything with plus or positive is in the numerator, everything with a minus in front of it is in the denominator, and then of course we pull the exponents out front. Now you might say, ooh, I don't have enough, or Ms. Bakken doesn't have enough room for a D, but that's because you're going to be doing that on your own. So that's using the same idea we just did, letter C, so that I can check to make sure you're understanding it when I check your note guide. Okay, so D is on you, and now we're going right to the back of this note guide, or you could pause me and first do D, that would make sense. This example number 2, it says, use the logarithm properties to condense. So now you're bringing things together. I do want to say, and I didn't mention it too much in that first one, because when you have one logarithm that you're expanding, of course you have the same base. But when you're condensing, you need to make, oh, I have a hard time writing up here. I'm going to bring this down. I'm going to erase that because that looks horrible. See, I'm so left-handed that I go right across the screen and it messes up. So make sure that everything has the same base before you decide to consolidate it. Because if it doesn't have the same base, you cannot obviously combine it. And here's an example which is not related to, or that's not logarithms, but it's the same idea, is if you have, let's say, x to the third, y to the fourth, you can't combine those because they have different bases. It's the same exact thing with logarithms. So if you have x cubed, x to the fourth, then you could say it's x to the seventh, but not unless they have the same base. Okay, so I think just for the sake of doing it, I'm going to just double check that we have the same bases. So notice letter A, we have base 2 all the way across, so that's good. Letter B, we have no bases shown, so we know it's base 10. Letter C, we again no bases, so we know it's base 10. And then letter D, we have again no bases, so we know it's base 10. So we're all good here. We can use our properties to combine these. Will there be an example eventually where you don't have the same base? Yeah, of course. And so that's why I just wanted to throw it in there. Now this, you're going to work exactly opposite of you did example 1. So you're going to actually take this right here. Oops, I have to, hold on, bear with me. I'm going to take this and bring it up there, and that's the only other exponent. So I have log base 2x plus log base 2y cubed plus log base 2 of 5. So I first get my exponent up where it needs to. So when you're condensing, you're doing the operations exactly opposite. So you're going to first use your power property of logarithms. Then notice everything's addition and positive, right? So we're talking about multiplication here. So we're going to go log base 2 x y cubed times 5. Now here's the thing. So it's x times y cubed times 5. But I'm going to put the 5 in front because that's just more proper. And that, folks, is it. So all you have is one log. So the trick to condensing is you end up with one log base whatever. So log, and then you have a composite of all of your other terms or factors multiplied or divided. And in this case, they were all multiplication. So let me just kind of, if you're like, okay, I think I got this. Let me show you this example, letter B. I'm looking across and I see there's a 3 here. I'm going to bring that up. There's no other exponents. So I have log base 2 plus log base 3 cubed. Now you're going to see why I did a lot of common logs, because then you don't have to keep writing the bases. Minus log base 9. Now, everything with addition is going to be in the numerator as multiplication. Everything else is going to be division or in the denominator. So I'm going to first bring the log, because I just need one log when I'm condensing. And if you want to write base 10 to make yourself feel better, that's fine. And then I have 2 times, because there's plus, 3 cubed. And it's not times 9, it's actually divided by 9, because the 9, the log of 9 is subtraction. Now here's the thing. Notice there's no variables here. We can go one step further and actually simplify this. So we know 3 to the 9th, or 3 cubed, excuse me, is 27. 27 times 2 divided by 9. When you do that, you end up with 6. So I'm going to actually simplify this and rewrite this as log base 6. So check this out. Letter B, it's this big long, log 2 plus 3 log 3 minus log 9. That actually just simplifies down to log base 10 or log of 6. Okay. So let's just kind of keep on going. I'm going to do these examples just because I find students, even though I feel this one's a little bit easier, students mess up on these more, and it's kind of interesting to me. So I'm going to do this one here. I'm going to first write it out where you have log 2 minus log a cubed minus log b. And now I'm going to use, so that again is my third property. That's what we do first. Now we just want a single log up front. And I see we have a minus and another minus. So really, you could write it with a fraction symbol right away. Upstairs in the numerator is going to be the 2. The denominator is going to be a cubed b. And folks, that is all there is to it. Again, we knew the a cubed b was in the denominator because of the subtraction. Last one. We have this is going up there, this is going up there, this is going up there. Oh, this is going to be a good one. So we have log 2 to the 5th minus log a to the 1/2 minus oops, that's 1/2, minus log b cubed plus log c. Okay, so I'm now going to consolidate it into one log, so I'm just going to write log way up front. I noticed that the positives are this one and this one, so those are going to be in the numerator, so 2 to the 5th c, and then the subtractions are a to the 1/2, b, and b cubed. Now, so that's it. Again, just look at what's in front of the expression. So in this case, if it's a minus, it goes in the denominator. If it's a positive, it goes in the numerator. And then we can, of course, simplify it a little bit more. So we have log 2 to the 5th. 2 times 2 is 4, times 2 is 8, times 2, and you keep going until you get to 2 to the 5th, which is 32c. So 2 to the 5th is 32c over a to the 1/2. I'm getting you ready for calculus. You could, I'm okay with a to the 1/2, but you guys know that's also the square root of a b cubed. In calculus, they have you switch it back into radical form, so I figured I might as well get you used to that. Okay, so there you go. Okay, that is how you condense using your power properties, or excuse me, your logarithmic properties. So now we get to the change of base formula. And it's interesting because when I teach this, it is very, very straightforward, but sometimes because it is so straightforward that students lose the meaning of it, really. So what this is doing, the change of base, is saying, hey, you know what? Log base BA. If you had a very complicated one where you could not do it mentally. So everything we've done so far, they've been nice, like 2 squared is equal to 4, 2 cubed. But what if all of a sudden you had like log base 23, 5? That's not going to be something you can do mentally. So what we can do is use this change of base formula. And actually, you know what? A better example is this right here. If you switch this over, 6 to what power gives you 11? There is no power. 6 to the first power is 6. 6 squared is 36. So we know that's somewhere between 1 and 2, but it's clearly not a nice answer. So that's where the change of base formula is really, really powerful. And this is then you can use your calculator. That's the great part about the change of base. So the change of base is this. We know our calculators have common logs and natural logs on it. And we can use the calculator if it is a common log or a natural log. So what we do is we change the base to a common log or a natural log. So what we do is we can do this right here, which is kind of just making sure you understand that you can change the base to anything. It doesn't have to be change it to the base 10 or change it to the base e. You can change the base however you want, as long as you take the log of the non-base a and divide it by the log of b. So I'm going to erase this so that I don't confuse you guys. So what I've just done is I've changed this general form right here to a common log right now. Or look at this, I could change it to a natural log, a base e, natural log of a over natural log of b. And then you can just type it in your calculator. Let's say we wanted a base of, I don't know, a smiley face. You can go log smiley face a over log smiley face b. So of course we can't use the smiley face in a calculator, that would be silly, but my point is that the change of base formula is a powerful tool where we can use the calculator to actually calculate logarithms by changing them from the base that they are to a base that is common or the natural log or anything else that would be helpful, like a smiley face. So these, excuse me, these are the ones that we do. Okay, so let me show you what I'm talking about now. Down here, I'm going to erase this because we know that this is not a nice number. We do know that it is going to be between, the exponent is going to be between 1 and 2. So we are going to use the change of base. What do? We go log, I'm going to just show you something now. Log, I'm going to say, let's change it to base 2. Base 2, 11 over log base 2, 6. Now this is a change of base. We just changed the base to base 2 instead of base 6. But this is not helpful in the calculator. This is not helpful. But I did want to make sure you understood what I'm talking about. Because again, what happens is if I show it too quickly, that all you have to do is go, log 11 over log 6 and type each one in the calculator and divide the values. That doesn't tend to be as memorable. So I just want to make sure that you realize you can change it to any base, not just the natural log or the common log. So I know the natural log of 11 is approximately, oops, that is an approximate symbol, hold on a minute, approximately 2.3979, and then log of 6. Ooh, actually, you know what? I did the natural log in mine. I was just using my sorry, you guys. I'm log of 11. I'm going to have to actually calculate that. So in my notes that I'm using as a reference, I chose to do natural log. In the video here, I'm doing common log, so I can't use my notes. Natural log is approximately 1.04139. And literally, I just typed in log 11. And then log, oops, again, you can probably even hear me doing it, log 6 is going to be approximately 0.77815. And then divide these out, and what you should get is a value of 1.34, which makes sense from what we were talking about, that we knew that the exponent had to be between 1 and 2, but closer to 1 because obviously 6 to the first power is 6, which is closer to 11 than 6 squared, which is 36. So this is the answer. So what is the log base 6 of 11? Or excuse me, log base 6 of 11? It's going to be 1.34 by using the change of base. Now I talked a lot on that one, so let me just kind of now show you how to do it really, really quickly. So this right here, again, you're going to use your calculator. I'm going to switch it over either to log or natural log. I'm going to choose natural log of 43 over natural log of 5. So I just switched it to a base of e. You use your calculator, and honestly, I wouldn't even do this approximation. I just type it all in your calculator, natural log 43 divided by natural log of 5, enter, and you should get a value. Make sure you're getting this with your order of operations in your calculator of 2.34. So what this is saying is 5 to the 2.34 is going to approximately equal 43. So again, what we're trying to find is the exponent that if you raise 5 to that exponent, you'll get the answer 43. And you can test it. 5 to the 2.34 gives you, well, 43.2, but pretty close considering we're rounding pretty harshly here. So that is a change of base, hugely powerful for evaluating logarithms that are not nice. I do want to make sure you realize, though, folks, that it's going to be very clear on when we do assessments, which ones are going to be on no calculator and which one's going to be on the calculator portion. So if I say don't use your calculator, don't use it because you want to get used to being able to do those exponents in your head. But if it does say use your calculator like this one here, use it because you need to be able to do it all. Okay, so if you have any questions, I'll be able to answer those in class. But thank you for tuning in. Take care.